Okay, so thank you for coming, and I want to talk about Gaussian 10 space. I mean, it was supposed that this weekend I will go to Manhattan, Kansas, that is the Little Apple, uh, but there were some issues, so I didn't go. Uh, and I wanted to talk about this, and as I mentioned to Melanie and Steve, this is a this is a culmination of a long discussion over probably around 30 years or so. Because see, um, in the, wait a minute, so what happened now? Uh, so, cannot make it this work. Oh, yeah. So the bulk of the harmonic analysis, the classical harmonic analysis, the Chicago School of Harmonic Analysis was a paper by Sigmund and Calderon in 53 of about singular integrals. And after that, there was a flurry of results. And this is, in a way, kind of a late result in 1985 by three big names, Koifman, Yves Meyer, and Stein, that they introduced a new um, kind of a space, and there are the 10 space. I will try to give some intuition about this. Unfortunately, this is kind of a little bit technical talk, but I am so excited about the result that I want to talk about it to whoever is willing to listen. So, so the 10 space in the classical case are very important because studying singular integrals in the classical case is always very painful, and these spaces develop an atomic theory, which means that the elements of the space can be written kind of linear algebra stuff, like a combination of atoms. And then, of course, to prove the continuity of singular integral, for instance, you only need to prove it for the atoms. So that simplifies greatly the work of that case, right? Uh, so of course, we, the people that work in Gaussian harmonic analysis, of course, every time that you see something in the classical case, you say, well, that was with respect to the Lebesgue measure. What can we say about the Gaussian measure that is completely different, right? And in 2012, Maas, Van Nierven, and Portal introduced Gaussian space, but we call it local Gaussian space because a 10 space, because they have to restrict to this region. And I will give you a better idea what this region means a little bit later, right? So that's why they are not working in the whole Rn1 plus, in the whole half space, but only in a certain region. That is especially one, and very much related with the Gaussian measure, right? So that was a very interesting paper because also they introduced something that hasn't been known until that is a Gaussian version of the witness covering lemma, that that is how you handle uh, a covering, the measure of the elements of the covering in the case of the Gaussian measure, right? So they were able to handle that. But yes, unfortunately, the fact that was only local was always a problem. And the way that they define these spaces did not follow the main idea in the classical paper by Kaufman, Meyer, and Stein. That was using maximal functions. Okay, so uh, so the so one of the key things was, well, we want to define maximal functions and area functions in the case of the, I'm sorry, not maximal function, area function is what I am talking about. But in order to define uh, area function in the Gaussian case, we need to consider uh, cones in the half space. And back in 1994, Liliana Forzani, that I have talked in the seminar before, with she was doing a postdoc with my advisor, Fabes, and they define what we call now the pencil type zone for the Gaussian cone, right? And yes, well, they prove the LP boundedness of that operator. So, but as we are going to see, that was kind of a problem, right? Uh, this the cone defined by them was not entirely satisfactory, right? So from that, from the evolution or the discussion of this uh, notion, we are able to define the now the Gaussian 10 space following the classical approach by Kaufman, Meyer, and Stein. That is to say, using area functions, and we are able to then get rid of the restriction imposed by Van Riemann and Portal to just stay in what they call local region, right? So then we have the dual endpoint 10 space, the duality with using Cartan measure, and establish a duality result in general. Okay, so this is, so let's now consider like a crash course in Gaussian harmonic analysis. Some of you have heard this before. So yes, we are considering the Gaussian probability measure in Rn, and then yes, we consider as usual the LP Gaussian spaces as it should be measurable functions that are LP integrable with respect to the Gaussian measure. Then there is an important component that is the Orten-Uhlenbeck semi operator, which is in the Gaussian world is the analog to the Laplacian. So it's the Laplacian, half the Laplacian, and there is this drift term, right? So what is this, the important operator in this case? Because, well, I mean, when you are working with the Lebesgue measure, the Laplace operator is formally self-adjoint in L2. Well, in this case, the Orten-Uhlenbeck is self-adjoint in L2 of the gamma measure, right? Or if you prefer, an extension of this operator. Okay, so then this is the natural symmetric Laplacian in the Gaussian context. The other ingredient is the Orten-Uhlenbeck semigroup, which is the semigroup generated by the Orten-Uhlenbeck operator. So formally speaking, these are the exponentials, right? So the Orten-Uhlenbeck is a negative operator. So similar to what you do in linear algebra, you can define exponentials of a matrix in the case of matrix in linear algebra, but those operators are bounded. In this case, L is an unbounded operator, but still you can make sense out of this semigroup. A third component is that the Hermite polynomials are the eigenfunction of L. That means we know exactly that the action of the Orton-Uhlenbeck over Hermite polynomial is minus their degree times itself, right? And then if I have a function in L2, the Hermite polynomials are a basis in a complete orthonormal basis there, then the action of the Orton-Uhlenbeck is, as you can see, is of this form. Is no wonder then that this is what you are going to see here is the action acting over the eigenvalue, right? And from there, with what is called the Meller's formula, we can get an actual an integral representation of the semigroup. This is what is called the Meller's kernel. And, if you put the exponential that is built in here together, you can write it in this form, which is, there are several versions of this. This is a nice one because this is pretty close to when in the classical case is the heat semigroup. The only difference, which is not only, but it's a big difference, is that the variable is dilated before you take the difference, and that makes things completely different. But in a sense, well, then the Orson-Uhlenbeck is the heat semigroup in the Gaussian world. And yes, then this was only a representation in L2. So when this representation, you can see that this makes sense perfectly in LP. But not only that, but you can prove that is LP bounded with constant 1. That means T of T is is uh, is a contractive semigroup, right? It's actually a Markov operator semigroup in the following the probability terminology. And then in the classical case, we have the heat kernel, the heat semigroup, and then we have the, the, the Poisson semigroup. Well, here is the same. You have, this is what is called the subordination formula, Buckner subordination formula. And from there, uh, if instead of this guy, you put the Orton-Uhlenbeck semigroup, then bingo, you get the Poisson-Hermite semigroup. And then, well, playing with this and the representation that we have of, we get this kernel, and looks very ugly, but you can handle that. And then, yes, because of the subordination, the Poisson semigroup have satisfied the same nice property that the Orton-Uhlenbeck. Okay, so this is like the minimum background to talk about what we are going to do. So here I said, well, we published in 2000, just 25 years ago, an article studying the Fabes for Sunny Gaussian cones, and we said that, the definition of area function is somewhat problematic due to the lack of a good definition of the cone region, right? And then, it has been a slow evolution of that problem. So now we will be more specific later. Okay, so first let's introduce this cutting function that is less than 1, that is 1 when x, the absolute value of the norm of x is less than 1, and it's 1 over x when the norm of x is bigger or equal than 1. So in other words, this is giving you, when x is less than 1, just give you 1, but when you move away from the origin, the function gets smaller and smaller, right? And then, well, for any beta, we can multiply this by beta, and then we consider the set of balls that are called admissible balls, which center at any number, in any place, and the radius RB, where RB is less or equal than this function. Forget about the beta, we can just think about beta equal to 1. So what this is telling you is that the admissible balls are going to be near the origin of area of radius 1, and when you move away, those has a tiny radius, right? Multiple of 1 over the norm of the center, right? So why these are interesting balls in the Gaussian harmonic analysis? Well, because on these balls, right, these balls, because of this condition, you can prove that the, 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 the measure of the ball is a multiple of the Lebesgue measure of the ball. That's the thing. On these balls, you can remember the Gaussian measure is an exponential, is the density of the measure. So here, because of the mx condition, you can control the exponential. So then the exponential is essentially constant, and therefore you can see essentially a multiple of the Lebesgue measure of the ball. And why this is important? Well, because, so this is what you say here. Oh, that the Gaussian measure is essentially constant, and in classical harmonic analysis, it was proved first for the Lebesgue measure, and then for the Lebesgue measure, was extended to measures that are doubling. What doubling means? Well, doubling means that the measure of the ball with the same center and radius twice the center can be controlled by a constant independent of the ball and the times the measure of the ball, the initial ball, right? So that's a doubling. And it happens that a couple of Italian mathematicians back in the 90s also proved that admissible balls are doubling, right? So in the case of the Gaussian measure cannot be doubling for any ball, but at least you can have that they are for this special ball, the measure is doubling, which makes perfect sense because, as I said, what you are looking at the end of the day is a multiple of the Lebesgue measure. Okay, so here comes the Gaussian cones. So these are the Gaussian cones for are of this type. You have y minus x. Let me just do the one. X minus y is t infimum m of y, right? This was the initial Forsani-Fabes cones. This is what we call, and there is a picture in a minute. These are the pencil-like type of cones. And well, as usual, sometimes little changes make things completely different. So here you see you are taking the cutting function evaluated in y, right? So this condition change with y. But a new cons is just evaluating at x, which is the center, is the vertex of the cone, right? So what is the difference of that? Well, the difference of that, see, this is the graph of the m function, right? M function is constantly equal to 1 until 1, and then it decays, right? So these are the Forsani phase Forsani cones. So it looks like a pencil, right? And is at the level at the same level. But the new cones follow the function, right? So it's like a tilted cone, pencil in a way, right? Okay, so it looks like a minor change, but is surprisingly not that minor change. What the Maas, Van Nierven, and Portal uh, knew? Well, the region that they consider is precisely this green region, right? They were only looking at that region, right? And yes, well, then the icons is only this tiny piece. Instead, since we are going to work in the whole uh, real, the Rn plus one, the cons is completely this, okay? So these are the cons, the new Gaussian cons. And well, as in the classical case, what you do is you take if you take a closed subset F, and you take the union of all the cons for X being in the set. Remember, X here is the vertex, is this guy, right? So, of course, in the classical case, the cons were cons, regions like this, and now, well, it's a little bit different. And then based on cons, and this is the thing why cons are so important, is that you define tens. This definition is the same definition and in the classical case. The only difference is in the classical case, here you are putting the classical cons. Here we are using the new cons, the Gaussian cons, right? And this is the 10 space. This is a Gaussian 10. I will give you a picture of that in a minute. So here you see you have an open subset, and for each open you take the complement, then it's closed. You consider the union of all the cons with vertex at all complement, and then you take the complement of everything. Okay, so what is the picture of that? Well, the picture of that is a tent. This, in the classical case, is always a 10. That's why it's called a 10. But unfortunately, or fortunately, we are not sure yet, uh, in this case, uh, depending of the radius of the ball, the 10 may have a chime, an infinite chime, which so there are two types, depending of the radius of the ball and the function m. Where you are, you may see very classical ones like this, but you may see things like this. Okay, so what? Well, then, and this is what's another important evolution of this idea, is that, well, we define the area function. Uh, Unfortunately, due to the time, we don't have, I do not have the chance to show you the evolution of this. Uh, but see, this is, you are taking a function in two variables, that is in Rn plus 1. You are taking the Lebesgue measure, and you are integrating with the cons. Sorry, not this, with the with sorry, these are the cons, right? In cons, right? Okay, so and there is in the case Q infinity, well, we have to take as usual something related with the sub of the function, and we have another function that is a little bit strange, which is taking the sub over all the balls, admissible ball of level beta, and you are taking here the 10th. We need this additional one, but the most important focus for us is this function. This is what we call the area function. This is the Gaussian area function. This is a new function, right? Okay, so what Forsani and Fabes define was for the Poisson and um, P equal to 2, Q equal to 2. So in a way, what they have is the S221 function. Well, it's in between S2 1 half 1 and F of 2 to 1, where F is the Poisson, right? Because see, remember that we are defining a max area function for any function defining this hyperspace. Okay, so yes, there. So from here and the original uh, uh, cones, we got to these guys. Okay, so what? Well, and this is what the following the classical case, we define the term space for functions, right? Such that the S, Q, alpha, beta, F are in LP, which means that we are using that this function is in LP. And yes, we take the norm of a function in the 10 space is nothing but the LP of the area function. And this is completely similar to what Kaufman, Meyer, and Stein did in 85. And it's different. I mean, as I already said, Mass, Van Nierman, and Portal give an alternative definition without the need, without using the 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 area function. Um, but they have the drawback that they have to restrict to the local area. And the case infinity, well, it's the same, but with the S infinity, which is the supremum over the cone. And then for the case when P is infinity, that we need to have this extra function C, which is not exactly following the same. So we need to use this guy for P equal to infinity. And yes, the norm is the LP norm always is the 10 norm is nothing but the LP norm of the corresponding function. Okay. So so what? Well, it's easy to prove. Well, it's not that difficult to prove that these spaces are Banach space. They are complete, right? Including the P equal infinity that has this special definition. And the important thing here, and this is also a discussion that we have since the 90s, right? We have been looking for atoms, Gaussian atoms, since the 90s, right? And so we have this definition. Um, so we have, well, the parameters Q between 1 and infinity, alpha, beta bigger than 0, and delta bigger than 0. So if we have a measurable function from the hyperplane to R, is a T, Q, alpha, beta, gamma, delta atom, if there is a ball such that for any Q bigger than 1 and less than infinity, the supremum is in the 10 space, in the 10 around the ball B. Remember, B has to be an admissible ball. And the norm for any Q is controlled by the Gaussian measure of B raised to the power 1 negative 1 minus 1 over Q. If the case in Q is infinity, remember this is just for Q bigger than 1 and less than infinity. So for Q infinity, we have the same condition for the support. The support has to be in the 10 cent based on B, but then this condition has to be changed a little bit to this one. But yes, if Q is infinity, this term is not here, but it's just the Gaussian measure of the ball to the negative one. So the atoms that Mass, Van Niven, and Portal had are coincide. I mean, the restriction of our atoms to the region D are exactly the one that they define. So we got atoms in the whole hyperspace, not just in the local region. Okay? And the tens that they define that are just restricted to the region D for an admissible ball will be the intersection of the 10 that we define in the intersection of our 10 in the region D. And then it can be proved that if we have a T1Q alpha beta atom, then is the atoms in their space and with this norm. Well, the important thing about atoms is that yes, this is the important thing that if you have spaces, for instance, the Hardy spaces, that was an important result by Koifman to find atoms in Hardy spaces. So because, well, if you have atoms and you have an element in the space, well, then you can find a sequence in little L1 such that the function can be written as a series of atoms. Not only that, but these coefficients, the L1 norm, which is this of the sequence, are controlled by a constant independent of f times the norm of the 10 norm of f. So this is one of the most important results in this paper. It's a very technically difficult, right? And the converse is also true. That is using the fact that the atoms are in the unit ball of this, the series associated with the sequence is absolutely convergent, and then we know that these guys are Banach space. Okay, so using that atomic decomposition of this space T1Q alpha beta, there is this result of immersion into classical Gaussian functional space. So the Gaussian 10 space P2 embeds continuously to H1, that is the Hardy space, the Gaussian Hardy space. The 10 space P2 is contained in LP for P between 1 and infinity, and the T infinity 2 of gamma is in the BMO space for the Gaussian measure. Okay, so for duality, we consider the natural extension of what is called Carlson measure, right? So if I have a measure mu, a Borel measure in Rn plus 1, we are going to say that it's a Gaussian Carlson measure if there are alpha bigger than beta bigger than 0 and a constant c, such that for any ball delta fixed Remember, these are not any ball, but balls, admissible balls. We have that the measure of the 10 based on B is controlled by a constant time, the Gaussian measure. Right? So this condition is equivalent, and this is the total variation, this absolute value of mu. And this condition can be proved is equivalent to consider this average over the 10 based on B, of supremum of all B's in the admissible balls of level delta. So this is mimic. This definition is a mimic from the classical case. What is the important or what is the main difference? Well, that in the classical case, you have here the Lebesgue measure, and these are any ball. Well, here we cannot put any ball, but ball that are admissible with respect to the Gaussian. But it's the same. It is really the same definition. Then we consider the set of all Carlson measures for the Gaussian with the norm, this guy, that we know is bounded. That is a Banach space, right? And then what we were able to prove is that the dual of 1 infinity alpha beta gamma is precisely the space of Carlson measures, right? And in other words, if you have this pairing between mu, a Carlson measure, and F, an element in this 10 space, you have this identification, so they work the same, right? So this is one of besides the atomic decomposition, this is one of the most important results in the paper. And then this is only for 1 infinity, but we also are able to prove it for P and Q, where P is bigger or equal than 1 and less than infinity, and Q is 1 Q infinity. Okay, so in that case, we have that this pairing for the 10 spaces, this duality one. And yes, I should say the P prime, Q primes are the usual one, right? It's the dual of P and the dual of Q. I mean, 1 plus P, 1 over P plus 1 over Q is equal to 1. And the same is true for the other one. Okay. So, so that's why I have insisted in that we should just concentrate in the case alpha equal 1, beta equal 1, because for a while we were thinking that given the using alpha and beta could give us a more flexibility, but almost at the end of finishing this paper, we realized that we can get rid of the alpha beta because they are equivalent. So yes, actually, but we have already written the whole paper, so we didn't want to change all the alpha beta there. So this is like a last result that the alpha beta plays actually no roles. All those norms are equivalent. So yes, you can stick with the basic case, alpha equal to beta equal to 1. So this is a very close to my heart because, as I said, this is a work with Liliana Forsanity, that was a postdoc of Jim Fays, my advisor, Roberto Scotto, that just recently retired, that was also a student of Fays and myself. And so this is like a final work. I mean, Liliana hasn't been working in harmonic analysis for almost 20 years by now. She got another PhD in statistics, and she's working in the statistics. She just published a book with uh, her advisor in statistics not long ago. But this, I mean, it started with the 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 cones, right? And the cones defined by her and Faith when she was as a postdoc, and the discussion about uh, 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 atoms has been done forever between us. And then, well, we finished this paper uh, in July, and well, we are very happy about this, right? So there are some other problems. Uh, so we treat the Gaussian counterpart of Coif-Montmeier-Stein, and so in following the same line of thought, and we were able to remove the restriction that in 2012 the paper by Portal and friends have imposed, right? Um, so we have the duality, uh, the Gaussian setting, the dual of the 10 space 1Q is described by the special functional that is the case because it's then the T infinity Q prime, so that's why we need to introduce this C function, while the dual of TPQ is described using these conical square functions uh, through T, as we show in the result, TP prime Q prime. Uh, so, so still, we were forced to consider this function. Uh, so what is the exact relation between them? We don't know exactly yet. We expect that they are equivalent for at least p between 2 and infinity, but it is not clear that. And we think that complex interpolation can be done. And also the Hardy space, the H1 Hardy space has been a very tough problem. We don't know if we can work with the area function, right? So, and for instance, something that I was thinking recently is that we have the atomic decomposition, whether we can use the atomic decomposition as in the classical case to prove continuity of the Gaussian singular integral using this atomic decomposition. This is not clear at all. Okay, so these are the reference, and this is the paper in which we study the cone and the area function that was 25 years ago. I cannot believe. This is the paper by Math, Van Nieren, and Portal. They have two, one for the witness covering, and the other one is for the 10 space. This is the one. Oh no, this one. Sorry. The fact that the Gaussian measure is doubling over just the admissible ball is a result by Maucheri and Meda, two Italian mathematicians, where they studied the BMO and H1 space. And so Maucheri, Meda, and Peter Sjölgren have a maximal function characterization of the Hardy spaces. That is an important result too. And Well, and that's it. The rest is so. Thank you for your attention. And as usual, this is if you want to know more about Gaussian harmonic analysis, uh, uh, we have a book. That, by the way, I just talked with the editor. I am planning to, in a couple of years, hopefully, do a second edition. Because including, for instance, this result, we in this book, what we have is the result by Portal and Company. So we have to replace that with a more fully result that is the one that we got, and there are other results. This was published in 2019, and there are really a bunch of results that are not in the book. So I am in conversations to do a second edition that uh, will include all the results in the recent times. Okay, so I agree. I'm sorry, it's a little bit too technical, but I hope that you get some ideas of how these things develop. Thank you. Any question or comment?
I have a question.
Yes,
Um, it seems very hard. Well,
it is. It is.
thanks for giving me that advanced math. So I just have a quick question about concept. So the tent is for the domain that looks like a
Yeah,
tent
in
shape.
hyperspace, the tens, right, are uh, the tens. In the classical case, the tens are always tens,
Yeah,
like this one,
yeah.
right? But since we have this function that is attached to the Gaussian measure, right, with this new definition, sometimes you get this, depending of the radius of the ball, but sometimes you get something that is
Alien
bounded.
thing.
Right, right,
Okay.
right. With
Um,
well, it's not that terrible because we know that the Gaussian measure towards infinity is very small, so that is not really terribly bad. But I have to confess, we were surprised that we get different things that the classical case.
then the area function. Is that the
Yes,
kernel? I'm not familiar with the notation, the terms. That
yes, is what?
is that a kernel? Can I think of that as a kernel? What is the area function? Like,
Now, the area function, I mean, in the classical harmonic analysis, I mean, the area function, you see, is defined over the cones, right? Over the cone.
okay.
So,
Can I think of that as a kernel over that cone or
well, here the kernel, yeah, I mean, is this is a restriction over the cone, but also you see, you have the Gaussian measure, and you have this extra term, right? You have this extra term. So this is kind of part of the issue, right? And I mean, to get to this point, there was a long evolution, right? But I mean, what this is trying to, I mean, in principle, what you are saying is that you take uh, you are integrating your function, right? Morally speaking, you are integrating your function over the cone, right?
yes,
But uh, then in this case, you need to integrate. We are integrating in Rn plus one, but then of course we have to integrate with respect to the Gaussian measure. But then you have to have this correction, right? This correction. So, for instance, in the case of the Forsani phase area function, the correction was up here, right? And
I don't see the I only see the Gaussian harmonic analysis textbook on the screen.
oh, is that so?
Um,
No, so let me hold it. Then let me. Uh, oh, oh, no. Oh, it was not. What about now?
Oh, now I see. Yep, yep.
Yeah. Okay. So see, the area function, this new definition. I mean, morally speaking, you are taking the kind of the LQ norm of your function defined on the hyperspace, right? With respect to
Okay,
the measure, the Gaussian measure, dt over t, right?
okay,
But there is this correction here, and this correction appears. I mean, in the classical case, that will be it, basically. But already for Sunny and Phapes, uh, they use the Poisson uh, semigroup, and then the correction is on is up here. So I unfortunately I do not have the time, but this condition here is essentially equivalent to this condition down here with respect to the
okay.
Gaussian. And this is a technical requirement. But essentially what you are doing is integrating functions over the cones, whatever the cones are, right? And this is,
Yeah, yeah.
so that I mean, there is also, uh, I mean, and the cones, that's the reason that also the cones, where are the cones? Here, no, this ones. The cones, I mean, in the classical case, why the cones are important? Well, the cones will be, in the classical case, the cones will be, uh, can I draw here? I don't know. Yes, probably. Yes. So the cones in the classical case are just like this, right? These are the cones, right? Since we have this
Mhm.
condition or with the M function, that's why the Forsanian phase got the pencil cones for the Gaussian, right? And the cones are crucial to control non-tangential convergence, right? Because when you say non-tangential conversion is that you can approach the vertex inside of the cone. You are not allowed to go outside like this, right? You are not allowed to do this, right? So the cones, that's why, for instance, if you uh, the paper by Maas, Van Nierven, and Portal, they refer to non-tangential maximal function because those are the one that controls the non-tangential convergence. That is important in our case. Okay? Hopefully that makes some sense.
Can you come back and do this for another hour each day over the next week so we can digest it fully? About what it takes, right? I mean, that was pretty awesome. And I feel like I'm just like getting excited about wanting to look at it more. And you're like, okay, we got to go now. Bye. So,
That reminds me, when I was a graduate student in Minnesota, uh, uh, Luis Caffarelli gave a talk in went there, and it was a very important talk. So, and then in the analysis seminar, the following quarter was just about explaining what Caffarelli did in 1 hour. So I agree. I'm sorry. I mean to
yeah,
to to crash to give
no
you
apologies
in
needed. That was
this
awesome.
result.
Thank you for sharing your work. And it's awesome. Keep working on it.
Yeah. Okay. So thank you for coming, really. I really appreciate it. I have been very excited about this result because, I mean, this is kind of a culmination, right, of long discussions over 30 years or so. So, and that is it's something. Well, it says that you are getting old. That's something that is, of course, true. But besides that, it's nice. Okay. Any other question or comment? Okay. So thank you for coming again. And
Thank you, Wilfredo.
And let's see what
Yeah.
well, there is Steve put the read AI meeting notes, so I don't know what they can share that.
If they send them to me, I will share it.
Let's see what it does. Okay. Have a nice weekend. See you next week.
Okay.
Thank
Thank you,
you.
Wilfredo.
Thank you.
Bye-bye.
Bye,
Bye.
everyone.